Well, welcome to day three of IQM Quantum School. We've been looking into what's behind quantum in general. We have been checking out both FTQC and near-term quantum algorithms yesterday. And on day three, we want to check out what it means to run things on actual quantum hardware in a more in-depth way, like what steps are actually involved that have been taking care of us on day one and two automatically. But if we want, we have more tighter control over these and can actually manually adapt things and optimize things. And that's what we'll do in two steps today. First, we'll continue with the view we had on the last 2 days, and we'll check out how we can optimize a given circuit for the hardware we have. And then second, we'll look into what is actually physically involved when we run things on quantum computers. And the sessions are not only content-wise divided into two, but they're actually personnel-wise also divided into two. We'll have Danny start first with a section on transpilation and optimizing circuits for the hardware, and then Nadia will take over for the more physics kind of view. I'm really excited to get started and learn more from Danny and Nadia, and I guess so are you. So without further ado, may I hand over to you, Danny?
All right, that sounds great. Thank you for the introduction, Stefan. It's really great to see everyone back here for an exciting day three of the Winter Quantum School. And we're going to start out today by talking about transpilation. So, as Stefan mentioned, um, so far we've just been sending a bunch of instructions to the quantum computer, and they just kind of run for you. But we're going to dig a little bit more into that today and really see what happens once you send your circuit to the quantum computer. So let's get started. If my slides will scroll. Okay. Let me see here. My slides are not scrolling. Give me just a moment. Um, oh, let's try that one more time. All right, and now we're up and running. All right, so what happens on a real quantum computer when you run a circuit? So the code that we've been writing over the past couple of days represents a quantum circuit, and it consists of a bunch of gates, right? You put in Hadamard gates, you put in X gates, you put in C0 gates, all these sorts of things. Then what ends up happening is that the circuit is converted into a different circuit. There are many ways to implement the same quantum circuit, and we'll see how some of those work today. But in particular, automatically, the circuit is transpiled. It's converted into an equivalent circuit that does the same exact set of gates using the effect of the same set of gates using a different quantum circuit that works with the quantum hardware's constraints and its gate set. So we'll talk a little bit about both the constraints and the gate set today. So one of the big things that we have to worry about on a real quantum computer is called circuit routing. So we've run into this a little bit yesterday. When we were trying to talk about our variational quantum algorithms and hardware efficient ansatzes, but it's a more general issue. So in general, when you're writing a quantum algorithm, we assume that any qubit can talk to any other qubit. So for example, if this is qubit 1 in our in the code that we've written, we assume that it can talk to qubit 2 and qubit 3 and qubit 4 and qubit 5 and qubit 6, no problem, right? A lot of times we assume that all of those qubits can talk to each other, and that means we can do things like apply 2-qubit gates that affect any 2 qubits in our system. Now, this is true for some quantum computers. For example, Sirius has essentially all-to-all connectivity. There's a little bit of a caveat there, but it's basically all-to-all connectivity. But not all quantum computers behave like that. For example, Emerald and Garnet only have neighboring qubits that can talk to each other. So in particular, if we wanted to apply some sort of gate between a qubit here and a qubit here, maybe say a CNOT gate, there's no direct way in which those two qubits can talk to each other on Garnet or on Emerald, because the qubits only talk to their neighbors directly. So these lines represent which qubits are connected by a coupler on the physical hardware. So we have to figure out how to implement our arbitrary algorithms using arbitrary connectivity on a QPU that doesn't have that physically. So what we have to do is something called the dynamical remapping or circuit routing. And we'll explain this in just a second, but the idea is that what we call qubit 1 on the hardware is not always going to be what we call qubit 1 in the program. We're going to be able to take qubit 1 in the program and have it correspond to several different qubits on the physical hardware, but we have to do something in order to do that. So we'll see how that works in just a moment. So imagine that we just have a quantum computer that has 3 qubits, which we're calling qubit 0, qubit 1, and qubit 2. And imagine that we want to do a CNOT gate between qubits 0 and 2. Well, as we can see, our hypothetical 3-qubit quantum computer has a connection between qubits 0 and 1, and a connection between qubits 1 and 2. But there's no direct connection between qubits 0 and 2. So what can we do? This CNOT gate is what's called a routing incompatible operation. There is no direct connection between the 2 qubits that we're trying to do a gate on. So what we have to do is something a little bit special, which is called to write a slightly different circuit. And this involves this gate which we've drawn here. So we haven't seen this gate before. What does it do? That gate is called a swap gate. Basically what it does is it takes the state 1, 0 and switches it with the state 0, 1. So it swaps the roles of the 2 qubits. It basically says that whatever state I had on qubit 1 gets turned into the state of qubit 2, and whatever state I had on qubit 2 gets turned into the state of qubit 1. So why is this helpful for us? The idea is the following. So imagine that we have in our program, we wrote down our quantum variable in CRISP, and it has 3 qubits in it. So we did quantum variable 3, and we have qubit 0, qubit 1, and qubit 2. Now maybe we would want to imagine that qubit 1 in the program corresponds to the physical qubit 2, or sorry, qubit 0. I'm sorry, let me restart that sentence. Qubit 0 in the program corresponds to the physical qubit 0. So the capital letters here are going to be what we're referring to in the program, and the lowercase letters are the ones that we refer to in the physical hardware. So we can't change which qubits are which in the physical hardware. But what we've done by putting this swap gate in is that we took whatever qubit was qubit 1 in the program, and we swapped its state over to the physical qubit 2. So this swap gate interchanges the roles of qubits 1 and 2 in the program. So if our program is telling us that we want to do a CNOT gate between the program's qubit 2 and the program's qubit 0, we can do that on the physical qubits 0 and 1, as long as we swap the role of the program's qubit 1 and the program's qubit 2. So these swap gates are essentially changing the labels that we associate to the physical qubits in the program. We started with physical qubit 1 being the program's qubit 1, and the swap gate made it so that now the physical qubit 1 is the program's qubit 2. So by doing this, we can connect any two qubits on the QPU. All we have to do is swap around enough so that if we had a very far away qubit, we can swap it to be close to the qubit we want to work with. The problem is that swap is actually very expensive. So imagine that we want to do this gate that we were just talking about, where we have some 2-qubit gate between qubits 0 and 2, and we want to do a swap between qubits 0 and 1 so that we can actually implement this gate. The problem is that the swap gate, in terms of what we can actually implement on hardware, is actually a lot of gates. Swap is written in terms of things you can really do on the hardware as 3 different gates. And then we actually have to swap back afterwards as well. So what we wanted to do as just 1 gate turns into actually 7 gates on the physical hardware. And so that's a lot of gates. That's a lot of error that we're introducing. And that's a lot of noise that we're allowed to introduce into the system. So we want to try to write our circuits in a way that avoids swap gates as much as we can. We want to work where all of the gates in the program talk to nearby qubits on the physical hardware as often as we possibly can. And in the lab today, we're going to actually work on that and see how some of those issues work. And we're going to try to optimize our circuit for the physical constraints of the QPU. Okay, so that's one thing that happens during transpilation. We have to decide how qubit 0 in the program turns into a physical qubit. Is it going to be qubit 0 on the physical machine, or do we have to use swap gates to make the program's qubit 0 turn into all sorts of different qubits on the physical machine? But there's another thing that we have to worry about when we're sending our program to the quantum computer, and that's gate decomposition. So in order to do that, let me give you an important piece of information about a QPU. In order to run any program we want, we need to be able to implement any gate or unitary operation, any gate that we want on our quantum computer. But on the physical hardware, as Nadia is going to talk about in a little bit, not all operations are simple. In fact, we really only have a small number of operations that are really well defined on our quantum device as voltage pulses, essentially. There's a set of simple gates that a specific quantum device uses, and these are called the native gate set. And they're the things that the software that's controlling the QPU actually knows how to implement. So the software controlling the QPU says, I know how to do only a very small number of gates, but the user wants to do, I want to do an X gate, an H gate, a Z gate, an S gate, a T gate, a C naught gate, a CZ gate, a Toffoli gate, all these different gates that we might want to use in our program. So we need to be able to rewrite any operation that we want to work with as a sequence of native gates. And we'll see how that works a little bit in just a few minutes. IQM systems have arbitrary X and Y rotations. So that's rotations on the Bloch sphere about the X-axis and the Y-axis as the native single qubit gates. And the only 2-qubit gate that we have native is controlled Z. So basically what that does is if both qubits, if both qubits are -1, or sorry, in the one state, it adds a phase of -1. So that's the native 2-qubit gate. Now, I just want to mention this expensive swap that I was talking about. The controlled NOT gate is actually not native. So in the real hardware, we have to apply even more gates than this in order to make a swap operation. So we want to avoid swaps as much as possible. So IQM systems, they only allow us to do X and Y rotations as the single qubit gates and CZ as the native 2-qubit gate. Okay, but is that a really bad constraint? Do we end up with a problem? So let's imagine that we have a QPU, and this is a very, very simple QPU. It's not an IQM machine. It's a very, very simple one. And the only native gate that it has is an X gate. So I'd like everyone to think for just a moment and think about if there's a gate that you can't implement on your QPU if the only thing that the software can send to the QPU is an X gate. Go ahead and put a chat in, or put the answer in chat. Good. So I'm seeing several people say that we can't do a Hadamard gate, we can't do a Y gate, we can't do a Z gate. Yeah, there's all sorts of different gates that we can't do. A Hadamard gate is totally different from an X gate. And what happens if I apply X twice? I get nothing. So the only things we can do with this really simple QPU is X and nothing. Because no matter how many times we repeat X, we're just going to get X or nothing. Okay, so that's no good. We're not going to be able to have a very powerful quantum computer with this overly simple QPU. Now, what happens if we also include a Y gate on each qubit? Is there something that we can't implement on our QPU? Right, so now we're able to combine the effects of the X and the Y gates. But are there still things we can't do? Good, I'm seeing a lot of good answers. Somebody actually said Z. It turns out that if you do an X and then a Y gate, that's the same thing as Z. But indeed, we can't do an S gate, we can't do a T gate, and in particular, we also can't do a C naught gate. We can't do any gate that involves two qubits talking to each other, right? Our native gate set only involves gates that talk to a single qubit. And so we can do many things to multiple qubits, but we can't make the qubits talk to each other. So now, so actually I just gave the spoiler for this exercise. If we can do arbitrary rotations about the X and Y axes on each qubit, it turns out that that's enough to do any single qubit gate. By combining rotations about the X and Y axes, you can get to anywhere you want on the Bloch sphere from any other point. So if we start at 0 and we do X and Y rotations, we're able to make a Hadamard gate, an S gate, a T gate, all of those things. But still, we can't make the qubits talk to each other. So we can't do a swap gate, we can't do a C naught gate, we can't do a CZ gate. Anything that requires the two separate qubits to talk to each other can't be done if we only have these native gates. So this is why having a well-chosen set of native gates is very important. We need to be able to do any operation we want, and we have to, and depending on the hardware, we have to make sure that we have enough gates that we're actually able to do any operation we want. So what that means is that our native gate set, the list of gates that is native, should be what's called universal. What does that mean? What that means, a set of gates is universal if we can do any unitary operation, or at least approximate any unitary operation as well as we want by only using the gates in S, in that set of gates. So we don't have to actually be able to exactly implement, say, a Hadamard gate, but we do need to be able to approximate it as well as we want. Essentially, this means that we have to be able to do any operation in practice. In particular, a universal set of gates for quantum computing can create superpositions. It can create entangled states. It can create gates with real and complex entries. So we need to be able to do different phase rotations. And we also need to contain more than what's called the Clifford group. Now, this is for those of you who are interested. The Clifford group is a special set of quantum circuits which can be efficiently simulated by a classical computer. So not all quantum circuits are hard to simulate on a classical computer. An arbitrary quantum circuit is hard to simulate, but the Clifford group is special. It's a special set of circuits that are classically simulable. And if you're interested in this, you should read up on what's called the Gottesman-Nil theorem, named after the discoverers of that theorem. Okay, so we know now that we need our native gate set to be universal. Is there only one possible universal set of gates? If that's the case, then we'd be forced to use hardware with a very specific set of native gates, and we'd be stuck saying the only allowed native set of gates is whatever this universal set is. It turns out that there are many different universal gate sets. Here's some examples. So one example is the C0 gate as the 2-qubit gate, the Hadamard S and T gates. There's another one on the right, which only has 2 gates in the universal gate set. All you need is the Hadamard gate and the so-called Toffoli gate, which you can look up if you're interested in that. But this center one is also a universal gate set, and that's what we use on IQM machines. It's the controlled Z operation, rotations about the x-axis by any angle theta, and rotations about the y-axis by any angle phi. So in fact, IQM's gate sets, or native gate set is universal, so we can do any quantum operations we want on this hardware by just using these gates. But now we run into a bit of a problem. So imagine that you want to do a circuit like the one I've shown on the top right here. So we have some Hadamard gates, some X gates, and a CNOT gate. So when we're writing a quantum algorithm, we want to generally be able to use these intuitive gates. We want to be able to write down a Hadamard gate or a CNOT gate. These things are really intuitive for us to work with because we can understand very simply what they do to our qubits. The problem is that the real QPU doesn't always use those gates directly, right? The native gates on an IQM machine don't include a Hadamard gate, and they don't include a CNOT gate. So what we have to do is use various identities to convert the algorithm circuit to an equivalent circuit that our QPU can actually implement. So that's the picture I've drawn on the bottom. So you don't need to understand the details of this, but I want to point out that these pairs here, you see there's this rotation around the y-axis by pi over 2, followed by a rotation around the x-axis by pi, it turns out that that is exactly equivalent to doing a Hadamard gate. And so you need to actually understand very carefully how to decompose your Hadamard gate into a product of x and y rotations like this if you want to implement a Hadamard gate. It's possible, but you need to be able to do that conversion, and the software will generally do that conversion for you. So CRISP does, when it sends the jobs to the quantum computer, does this transpilation procedure where it turns a Hadamard into these two gates for you. Now, I just want to highlight as well that this piece here is an X gate. So it turns out that an X gate is native to the to an IQM machine. It just consists of a pi rotation about the x-axis. And the C naught gate is this somewhat messy thing. So you see here the 2-qubit gate in the center here is a controlled Z operation instead of a controlled not. And then we have to sandwich with some other gates, which, if you look closely, are actually Hadamard gates. So if you sandwich a controlled Z by some Hadamard gates, that gets you a controlled not. But the important thing is that controlled Z is native to the machine, and controlled X is not. So we have to rewrite it like that. Okay, so to summarize what we've learned, transpilation consists of routing the circuit to the connectivity of the QPU and decomposing its gates into the native gates. So we need to make sure that we're actually doing gates on qubits that are able to talk to each other on the machine, and we need to decompose the gates into the ones that we know how, that the software knows how to send to our machine. So that's the summary of what we've learned for transpilation. Okay, so that's all I've got for the lecture for transpilation. So we're going to shift over to the day 3 part 1 lab. We're going to do day 3 part 1 lab, and then we'll come back to lecture, and Nadia is going to talk to you about the physics of the quantum computer in a little bit more detail, and then you'll have a lab portion for that as well. So the lab is available here. And I just want to say, please don't worry about debugging everything yourself during the lab session. It's going to be more useful to you if you follow along with what I'm doing and then debug later on your own. If you still need help, you can use the Discord, which perhaps we can put a link to the Discord into chat for those of you who haven't signed up for the Discord yet. But it will be more helpful to you if you don't spend a bunch of time trying to debug anything, and you can actually just follow along what I'm doing. So I'll leave this link up for a little bit, and then I'll switch my screen share over. All right, I'm going to switch over. Um, everyone should have access to it. It is set to have sharing. My co-hosts, are you seeing an access problem as well?
Let me check, Danny.
Let me see here.
So I can access it. Let me share the link.
Oh, you know what? I see the problem. Hang on.
Okay.
I did in fact, I think we, let me see. I think I might have I might have put the wrong link in there. My apologies.
Okay, no worries.
So let me
I'm
put
sharing
that in
the,
chat.
yeah, I shared the one I can
Um,
access in the chat.
let me see. Um, one moment. Oh my goodness.
Oh, sorry, I should
Here,
have shared.
try this link to
Yeah.
everyone.
Okay, great.
Okay, I think we're working now. Let me just check exactly what's happening here. Oops. The original link was to the solutions. That would be the problem. Yeah, the original link I had was, or the one that I had opened up was to the solutions. Okay, so is everyone, so hopefully everyone should see a notebook that says Winter School Day 3, Part 1 Transpolation
Yeah,
right now.
I think people are saying in the chat that it works now.
Okay, good. All right. So now everyone should be able to see this. So as a reminder, we're going to change our runtime to 2025.07 as we did the other days and get some packages installed. Hopefully, any issues with NumPy versions and things like that should be set here. Um, but we'll get that all set up. Okay. So what we're going to do in this lab is we're going to create a GHZ state, and we're going to keep in mind exactly what is happening on the quantum computer. So in particular, we're going to be paying careful attention to routing. So we want to make sure that we do something that is routing compatible. All right. Let me see here. Good. All right. So that's going to take a little bit of time to connect and run the installation. So I just want to mention that a lot of the things that we're doing today are going to look a little bit different from things we've seen before. And the reason for this is that custom choices of qubits, um, the way that we're going to implement the custom choices of which qubits we're working on today is going to be done in Qiskit instead of in CRISP. So some of the syntax is going to look a little bit different. Um, all right, we are almost connected. Okay, so the first thing that good, we're now connected and my packages are going to start installing. So the first thing we're going to have to do is connect to the QPU. Now, today, because we're talking very carefully about which qubits are talking to which qubits, this lab is actually not going to be very interesting on Sirius, because Sirius doesn't have routing constraints. On Sirius, all of the qubits can talk to all of the other qubits. So I recommend using either Emerald or Garnet for this lab. And you can adjust which one you connect to by changing this line, this little bit. So if I wanted to connect to Garnet, I just put Garnet here, or you can leave it as Emerald. That is totally fine. All right, so I can't run this quite yet because my packages are still installing. That'll take just a moment. Okay. So actually, yeah, let me just pause while that's happening so that other folks can do that as well. And I can't go much further without that being done. And just a reminder, you will need your API token in order to connect to Resonance. We have a lot of packages to get installed. So actually, while this is happening, I also want to show you a little something on Resonance. So if I look, since I decided I would use Garnet, I'm going to pull up Garnet, but this works for Emerald as well. If you look on the Resonance website and you click on one of the machines, you get something that looks like this. So make that a little bigger. So what is happening here is these different colors are telling us about how noisy the qubits and the couplers are. So green is better. So qubit 12, for example, here doesn't have much noise, whereas qubit 8 over here has a lot more noise. So one of the things that we're going to want to pay attention to when we're running quantum programs is not just which qubits talk to which qubits, but we also want to pay attention to which qubits have low noise. And this fluctuates a little bit over time. If you change what's in this menu here, it will give you different measures of the noise of the qubit. So for example, qubit 20 has a really good, doesn't have much noise according to this measure, whereas it has a little bit more according to this measure. But in general, we're going to want to try to run our programs on qubits that don't have much noise and using couplers that don't have too much noise either. So let me get my restart session done. And once that's done, I'm going to run my installs one more time to make sure everything's running properly. There we go. Just got a few more packages to install, and then we'll be ready to go. And we see this a second time, and we're going to cancel it. Oh, I think because of NumPy, we actually might need to reinstall it to restart the runtime a second time. Let's check. We're almost done here. Sorry about my scrolling. All right, we've run everything there. Let me actually just restart my runtime one more time just to make sure. Okay. So once that finishes restarting, we can connect to the quantum computer. And as usual, we're asked for our API token. So go ahead and get your API token ready. There we go. All right, so that is running. So now we can actually access the system. So what this code is going to do is it's going to show us what qubits we have to work with and what qubits and how they're connected to each other. So here's Garnet, and it shows us the qubits like this. So let's actually take a careful look. How does this set of qubits compare to what we see on the IQM Resonance website? Well, let's notice that the qubits start from 0, 1, 2, 3, 4, 5, 6, so on and so forth on this diagram. But if we go over to the Resonance website, On there, the qubits actually start being labeled at 1. We have 1, 2, 3, 4, 5, 6, 7, so on up to 20. So the labeling in the software is from 0 to 19, and the labeling on resonance is from 1 to 20. So that's something that we're going to have to be a little bit careful of as we run our quantum circuits. So make sure that you're aware that the way that resonance labels its qubits are a little different than the way that the software labels its qubits. Okay. So the first thing we're going to do is we're going to create a GHZ state, a Greenberger-Horn-Zeilinger state. Now, we saw this in Stefan's lecture on Tuesday, and it is a state that looks like this. It's an entangled state where we have three qubits that are either all in the 0 state or all in the 1 state with probability 50% for each. And we're told how to do this process. In fact, this is all done for you here. We start by creating 3 qubits. Now, because we're working in Qiskit here, this looks a little bit different than what we've seen before. Instead of using quantum variable, we use quantum circuit. So this is just slightly different syntax. And instead of saying h of our qubits, we have to write it in this slightly different syntax where we have qc.h. And so what this is doing is this is saying apply an h gate to the 0th qubit of the quantum circuit QC. So what we're doing is we're applying a Hadamard gate to one of the qubits, and then we're applying a controlled X qubit or gate between the 0th qubit and the other qubits that we have. Okay? So this applies a control X or control not, same thing, gate between qubit 0 and each other qubit in QC. Then we measure our qubits, and so our circuit looks like this. We apply a Hadamard gate and then some controlled NOT gates. So this is something we've done before, but the syntax just looks a little bit different today because we're working in Qiskit. Now, if we want to do this, this code will run and plot the results of this circuit. So this is what we've done. This is what we've done before in CRISP, but here the important thing that we're going to be using a lot today is this transpile command. In that transpile command, we're going to be able to modify things like which qubits we're using. So right now, we're just using automatic options. And so if we run our job, it's going to run it on resonance because the backend is the backend that we defined earlier, which is what we connected to on resonance. So this is actually running on the actual quantum computer. And here's the results. We see that with almost 50-50 probability, we get the qubits to be in state 0 or state 1, and there's a little bit of noise where we can end up in other states. But that's pretty good, right? Just automatically running it, we mostly get all of the qubits in state 0 or all the qubits in state 1. So far, we haven't done any coding ourselves. We're just kind of seeing a little bit of how the syntax is different when we're working in Qiskit. Okay. So let me pause briefly and see if there's any live questions that we should answer before moving on to the part where we actually need to do some coding. Okay, so the first thing that we really want to explore is what happens if we're working on 2 different sets of qubits. And we want to see if we can get better performance, right? So here, there's, 200, 300, 400, 500, 600, about 700, about 800 of these counts were not in the 000 or the 111 state. So those are all noise. Our circuit is supposed to prepare a state where the qubits are either all in the 0 state or all in the 1 state, and it wasn't perfect. So we want to see if we work on two different sets of qubits, if the noise will be different. So let's do that. So what's happening here is that we've got two different lists of qubits. So one list of qubits we've chosen for you. It's qubits 1, 2, and 5. So if you're working on Garnet, that's these three qubits here, 1, 2, and 5. And you see that they talk to each other. And if we're working on Emerald, for those of you who chose to work on Emerald, that's qubits 1, 2, and 5 over here. So these three qubits are also connected to each other. I'm just going to work on Garnet, but you can do the same idea on Emerald as well. So if we look here, these qubits are in kind of like grayish, like a grayish green state. So T1 here is a number that the higher it is, the better, the less noise that you're going to have on that qubit. So these qubits have kind of middling T1s. They go between 29 and 40. So we might want to choose 3 different qubits that have better T1s. So if we look at just the colors here, we can kind of get a sense of which qubits that might be. In particular, this qubit 12 here is looking pretty good. It's got a T1 of 74 microseconds. And it's got some neighbors that also have pretty good T1s. So maybe type into chat a set of 3 qubits that we might want to work with that might have less noise than qubits 1, 2, and 5. Oops. Good. I'm seeing a lot of good answers here. So 11, 12, and 17, or 12, 17, and 16, those are all excellent choices. Because these all have pretty low or pretty high T1s, and the couplers between them are also pretty good. Oops, I closed Garnet. These couplers are also green. It's important for the couplers to also be good. We want to be able we don't want to do too much noise when the qubits are talking to each other. So you'll notice that this connection between qubits 11 and 12 is a bit noisier than the connection between qubits 16 and 17. So there's 0.17% error here, and there's 0.35% error over here. So it's best to use 12, 17, and 16. The qubits are great, and the couplers between them are also good. So what we're going to do is we're going to run the same circuit on qubits 1, 2, and 5, and qubits 12, 17, and 16, and we're going to see the comparison between them. So let me put 12, 17, and 16 in here. Now, there's an automatic, the nice thing here is that we actually get to use the resonance names for the qubits here. So 12, 17, and 16, oops, are in the code here. And the reason is that we have this method that says qubit name to index. And that automatically takes care of the fact that the names in resonance are not the same as the names of our qubits. So it's going to handle that for us. So we can just put in the qubits we want, just like this. The attendance link will be coming up. Don't worry. All right. So we've now picked our 3 qubits that we want to work on. And when I run this cell, what the output does is it tells us which qubits are coupled. So in particular, for qubits 1, 2, and 5, we saw on Garnet that qubits 1 and 2 were coupled, and qubits 2 and 5 were coupled. Now, this is where that numbering scheme gets messed up. 0 in the software is 1 on resonance. 1 on the software is 2 on resonance. 2 and 4 on the software is 5 on resonance. So when you're interpreting the output, you have to be a little bit careful here. But this is telling us that indeed, the qubits that we expect to be coupled are the qubits that we expect, or that are actually coupled. So now what we're going to do is we're going to make the quantum circuit that creates the GHZ state on the first 3 qubits that we chose. So what we need to do is we need to do a Hadamard gate on some qubit, and then we need to do a C0 gate or a CX gate on the other qubits. But we want to choose those carefully. In particular, we want to choose our CX gates so that they're actually coupled on the machine. So let's go back to our map. We're working with qubits 1, 2, and 5. So we need to do C0 gates between 2 pairs of qubits. We had better not choose a C0 gate between qubits 1 and 5. That would be bad. Why? Because there's no coupler between qubits 1 and 5. And so if we actually try to put in that coupler in the circuit, we're going to have to do a bunch of routing stuff so that those qubits can actually talk to each other. And the circuit on the hardware is going to get more complicated. So our aim is to make it so that the CX gates happen between qubits 1 and 2 and qubits 2 and 5. So we want CX gates to be between 2 and 1 and 2 and 5. So let's take a look. We have 3 qubits and in our circuit, and they're ordered like this. So it's qubit 1, qubit 2, qubit 5. So qubit 1 is going to be, and so that means that QC0 is qubit 1 on resonance. QC1 is qubit 2 on resonance. And QC2 is qubit 5 on resonance. Now, this is important here. QC just has 3 qubits. It doesn't know, sorry, this is QC1. QC1 doesn't know about any of the other qubits on resonance because it only has 3 qubits here. And so that means the only qubits that it knows exist are the ones we specified here. So out of all the qubits on resonance, this one is qubit number 4, but for our quantum circuit, where we're only paying attention to the existence of 3 qubits at all, we're just listing them in order, the 3 ones that we chose, 1, 2, and 5. So we want our CX gates to couple qubits 2 and qubit 1. So that looks like this. So this is CX between QC0, sorry, QC1, 1, which is qubit 2, and QC1, 0, which is qubit 1. And we want our CX gate to be, so this is CX between QC1, 1, which is qubit 2, and QC1, 2, which is qubit 5. So that's how we set up the couplings between the specific gates that the specific qubits that we want. We make a quantum circuit that has the right number of qubits, and we pay careful attention to the order of the qubits that we're looking at as we've specified them above. And then we want our Hadamard gate, and that has to be the one in the first argument here. So the circuit only works if the qubit that is the control, so the first one in this argument, has been Hadamarded first. So Hadamard on QC1, 1, which is qubit 2. So let's take a look at our circuit. I'm going to run this. So actually, let me do that. Let me do something slightly different first. This is just for demonstration purposes. You don't have to follow that. Oh, uh-oh. This should be QC1. I apologize. I think some of you probably have QC. I think I was typing QC instead of QC1. That should all be QC1. So let me just put in an extra draw command here for a moment. And this is just to illustrate something. So without doing any transpilation, we have this circuit. It applies a Hadamard gate to the software's qubit 1, and then C0 gates over here. But now, this transpile command is telling us that we are going to put this, this circuit onto the qubits that are specified by what we called reduced coupling map 1. That was the couplings that we had that involved our set of qubits 1. So that's where that part, reduced coupling map 1, is where we pass in this list of qubits that we're working on the physical computer. So nothing up until this transpile line knows anything about Garnet. Once we put in this reduced coupling map 1, that's what tells us about Garnet. And so if I draw the transpiled circuit, we're going to get something quite different. What we see instead is that on the physical qubits 0, 1, and 4, we have a circuit. And you'll also notice that there's no Hadamard gates and there's no CX gates. Instead, we only have native gates. So the software is automatically converting our CX gates into CZ gates and a bunch of other stuff happening here. And it converts this Hadamard gate into some stuff that happens on qubit 1. So this transpile function is doing a lot of work. It's telling us which qubits we want to work on, and it also converts all the gates we used in the circuit into gates that are native to the IQM machine. Okay. So the next thing that we're going to be asked to do, oh, and you see that all of the qubits on Garnet show up here. We aren't doing anything with most of the qubits on Garnet, but that's okay because we only need 3 qubits right now. Now, the next thing we want to do is adapt that code, same code, but we want to make a GHZ state out of this qubits in set qubits 2. So let's see how we have to change the code to look at the second set of qubits that we chose. So let's go back up to which qubits we were looking at. The second set of qubits that we were looking at were qubits 12, 17, and 16. So this is going, so now, once we make, okay, so sorry, let me get that commented down here, which is qubit 12, qubit 17, and qubit 16. So now we want to make a different quantum circuit. And So the idea here is that the qubits are now going to correspond to the 3 that we chose in the set qubits 2. So instead of qubits 1, 2, and 5, we now have qubits 12, 17, and 16. So right now, the software doesn't know about any other qubits existing, just those. And so all of this is going to be for QC2 instead of QC1. So we just have to change that. But now the question is, which gates do we want to connect with CX gates? Well, if we look at the diagram, we see, sorry, let me get back to that diagram, that qubit 17 is the one that's connected to the other 2 that we were looking at. So we should probably make it so that qubit 17 gets connected to qubit 12, and qubit 17 gets connected to qubit 16, because those are the ones that are physically connected. So now we just have to make sure that we're applying the CX gates in the right place. So qubit 17 is the second one in the list. So that's QC2 number 1. And QC2 0 is the 12th qubit on resonance, right? We've got this mapping that we wrote down by listing our 3 qubits like this. So this is good. It actually gives us the CX gate between qubit 17 and qubit 12. And similarly, you can check that this one, oops, this is QC2, that this one gives us the connection between qubits 17 and 16. And then the one that we need to apply the Hadamard gate to is the one in the first argument here. And so that's qubit 17. Everything is good. So let's see what happens. Oh, there's something important here. We also need to specify when we're transpiling which qubits we want it to work on. So in particular, we want it to work on the second set of qubits, which was this thing that we called reduced coupling map 2 up above. This was the thing that we produced that told the machine which 3 qubits we're using, and that those are qubits 12, 17, and 16. Reduced coupling map 1 tells us about qubits 1, 2, and 5. Reduced coupling map 2 tells us about qubits 12, 17, and 16. So if I run this code, we'll see that now the physical qubits that it works on are 12, 16, and 17 in resonance labeling, and 11, 15, and 16 in software labeling. So this is running a circuit on a different set of qubits. Okay. So the key difference between the 2 blocks of code is that we put in reduced coupling map 2 instead of reduced coupling map 1. That's what tells us about the different qubits. We had to be careful to make sure that everything was ordered properly so that we're acting on the qubits that we actually want to be acting on. So we had to make sure that our list corresponded in the correct way to the software's qubits 0, 1, and 2. Okay. So I want to point out that there is a little bit of confusion. There's a strong potential for some confusion here, which is that the software has 2 different labeling schemes for the qubits. If you don't tell the software about all the qubits on Garnet, then when I make a set of 3 qubits, you only have 3 qubits. You only have 0, 1, and 2. And so you have to manually keep track in your head or in the comments like this, which ones you want to correspond to which physical qubits on resonance. Now, separately, when you tell the quantum computer about all of the qubits on Garnet, there is an automatic labeling here, which is the 0 through 19 business. And so this 0, 1, 2 that we have up here are you can think of it kind of like the programs 0, 1, 2, and the 0 through 19 are the hardware's 0 through 19, except unfortunately, Resonance also likes to refer to those same 20 qubits by 1 to 20. So there's two different schemes for labeling all 20 qubits on Garnet, unfortunately. But you can think of the 0, 1, 2 that come from this quantum circuit thing as being the program's labeling. Okay. So that's some potential confusion. You should definitely play around with these things and try to get used to them yourself. So now we can run both circuits. So this one runs the circuits on the noisier qubits, qubits 1. So that's QC1 transpiled. And this cell runs the circuit on QC2 transpiled, which are what should be the better qubits. So let's see what happens when we run these two circuits. Oops, uh-oh. Oh, that's what happened. I forgot to tell this thing to measure the qubits. At the end of the circuit, you have to do QC1.measure all. That tells it to actually go ahead and measure the state of the qubits. If you don't tell it to do the measurement, it won't measure anything. So that line has to be in both of our circuits here. So a little bit of debugging there. Okay. So if we try again, now we should be able to run this job on Resonance. And hopefully Garnet didn't pick up too much of a Q in the meantime. There we go. Okay, so we see that in the 0, 0, 0 state, we have about 4,300 counts, and in the 1, 1, 1 state, we have about 4,700 counts, with the rest of them being noise. So let's see what happens when we run on the qubits that we think are better. We're going to do exactly the same thing. Let's see, so that's about 2, 4, 6, 7, 8, about 950 noise counts. And when we run on the qubits that we think are better, it actually doesn't do much better. We still get about 750 noise counts. So that could be random chance, just because noise is random. Or there could be something else going on with the qubits. This worked when I ran it before. Of course, it ends up happening that we get the noisy one this way. Or something ends up being noisy. So I'm curious what happens if I run that job again. All right. But that's the general idea. So you can choose which qubits you want to run on and hopefully avoid noise. So while that's running, I just want to, oh, it still ended up being about the same. That's peculiar. I'm just going to double check that I didn't make a silly mistake. Nope, those circuits look right. That's peculiar. I don't know why those qubits weren't as good as it looked like. So maybe try experimenting with different sets of qubits and see if you get some different results. All right. So I just want to mention that the homework for today is going to be to experiment with routing. So you're going to want to make a big GHZ state with more than 5 qubits. Now, I do want to mention conceptually why this is an interesting problem. So if we look at the quantum circuit like this, if we want to work with 5 qubits, we can have these 5 qubits, for example, in the center here, 10, 11, 15, 9, and 5 all talk to each other. Well, they can all talk to qubit 10, and that's actually enough to make a GHZ state. However, if we want to have more than 9 more than 5 qubits, we're going to have to find a different way to make a GHZ state rather than having a CX gate that only talks to qubit 10 and something else. Because if we want to add states into the GHZ state, we have to talk to them with one of the states that's already in the GHZ state. So if we want to add qubit 19 into the GHZ state, we need to do a CX gate. But we can't do a CX gate between qubit 10 and qubit 19 without running into routing problems, which is solvable, but it's going to be noisier. So the homework is going to walk you through creating a GHZ state on 9 qubits in a way that accounts for routing constraints. So the aim is going to be to not have to use any swap gates when you're constructing this big GHZ state. And there you should see a pretty big performance difference when you do it in a way that's routing compatible and a way that's routing incompatible. So you can go ahead and work through that for the homework today. All right, so that's all I've got for the lab for now. So we're going to take a 10-minute break and then come back to talk about the physics of the quantum computers with Nadia, which should be very exciting. Really dig into what's physically happening on the quantum computer. But in the meantime, there will be some of us sticking around to answer questions during the break. So come back at about 20 or 21 after the hour if you're in most time zones. And for those of you in which it's currently 42 after the hour, come back at, what is that, 50 or 51 minutes after the hour. The attendance link will be coming. Yeah, the queue might be big. Take a look at the queue for Garnet and for Emerald and decide which machine you want to run on. You might be able to get a shorter queue by running on a different machine.
Danny,
Yes.
someone is asking if you can repeat what is the homework again.
So the homework, so you'll get attendance credit for running any of these jobs on Resonance, but the homework is described here. You're trying to make a big GHZ state that doesn't require swap gates. So the goal is to make it so you have a routing, you want to compare a GHZ state made a naive way, which looks something like this, where all the control gates are controlled on the same qubit. And then you're going to try to construct a GHZ state in an efficient way that doesn't require swap gates. So you're going to choose your 9 qubits on the machine very carefully, and then choose the way that you apply the gates so that you don't have to do any swaps in the process. So that's what the idea of the homework is. The break is 10 minutes, so it's going to be, we're going to restart at about 20 or 21 minutes after the hour. All right, so I see a lot of people are running low on credits. So the homework doesn't make a lot of sense on Sirius, but the first part that we went through in the demonstration does make sense on Sirius. You're going to have to be careful if you're running on Sirius, though, to make sure that you use reasonable qubits. In particular, some of the qubit numbers on Sirius don't run. So qubits 6, 7, 12, 14, 18, 22, 23, and 24 don't run on Sirius. So make sure on Sirius that you're choosing the qubits that actually work. So you want to look very carefully and decide which qubits you want to run on if you're doing this on Sirius. If you get a warning about measurements, this was a bit of code that I forgot to put in the first time. Make sure that your quantum circuits include a line that looks like this, qc.measureAll. That is actually telling it that you're going to make a measurement. The attendance link will be coming. So if you're not sure which qubits do and don't run, you can check on the Resonance website. So if you're running on Sirius, you can go ahead and look on the Sirius dashboard. So if you see something that looks like, if you can't see Sirius, there'll like this. There's a little arrow. Let's see, oh my goodness, I have too many things going on my screen. Can't see very well. So you should be able to scroll over to see Sirius. And why is it not scrolling for me right now? If I make the window bigger, at least, I can see Sirius. Click into Sirius, and then any of these qubits with the little dashed lines, you can't use those numbers. You have to use the numbers that are colored in. So it's still a 16-qubit quantum computer, but the numbers are a little bit funny for which qubits are actually running on Sirius. So make sure that you use some of the colored in ones. You can check yourself. So you can think routing-wise on Sirius, you can think of all of the qubits as being connected to all of the qubits. The reason is that all of the qubits are connected to this central resonator. So this is a very different topology than you get for the other two machines, Emerald and Garnet. There's an interesting question here, which is what considerations do people use when they're choosing a universal gate set for their machine? Yeah, it does correspond to the qubit technology. So superconducting qubits have a different native gate set, and even different implementations of superconducting qubits might have different native gate sets. So it really just depends on the physical hardware and the electronics and how you're interacting with the qubits. Different qubit architectures and hardware will all have different native gate sets. It's really just how do you design the electronics and the operations that make sense with the physical qubits themselves.
Hello there. I think it's time to start
So it
again.
is.
Am I right?
Absolutely, I think it's time.
Okay, great. So, welcome back, everybody. I hope your break was relaxing enough. So let me start by sharing my screen. Here we go. Okay. So today you're lucky enough to have actually two lab sessions because one was not enough anymore now that you are becoming more experts in the quantum computing field. So we thought that was actually interesting to give you an idea of what is actually happening behind the scenes every time you write like a gate into your quantum circuit or you're measuring your qubits. What is actually the quantum computer doing? So we will try to do this with some physics, but not much, hopefully. Great. But yes, first, the moment you have all been waiting for is here, because please find the attendance form with the QR code. But I would actually also ask Danny or Stefan to please share the link in the chat also, so people can find it more easily. Okay. I'll still give you some seconds to scan or to copy the link from the chat. Can I actually have yeah, let me also open the chat. So, okay, so the link is there. Then let me go. Let me proceed. Okay, so in this past 2 days, I hope you have become familiar with words like qubits, superposition, measurements, and things like that. And I want to stress here that especially you have become familiar with how a qubit behaves, when it is alone. So you can actually put a qubit, a single qubit, in a superposition of two basis states. And we have seen that we have actually a very useful and intuitive visualization with the Bloch sphere here represented. So this vector and the point on the sphere represent the state of the qubit. And you can measure this qubit to actually know in which state it is. But if you have prepared it in a superposition, you know also that the outcome will be always 0 or 1 with a certain probability. And this is what we call the collapse of the state of the qubit, of the quantum system in general. Because to measure again the qubit, you will need to re-prepare it in the initial state and then perform the operations that you had and then measure again, because you cannot perform repeated measurement on the same qubit after the collapse. But this is not all. This is already very interesting, but it is not all, because we have seen that when we consider qubits together, so many qubits starting from 2, then you can have other very interesting properties like entanglement. And this circuit here on the bottom left by now should be also very familiar, because we have seen this many times and we will keep seeing this today also for our more physics related lecture. Because so we know what this gate here, this is Hadamard gate. We know what this is. This is a CNOT gate, also called CX gate. And we know that these two together, so applying first, preparing a superposition state and then applying a CNOT gate, this will give us an entangled state. And this 2-qubit gate here is also called an entangling operation, because it enables entanglement between the qubits. And what you see here is, though not the output of this measurement, because we wouldn't have so many basis states, it's the output, it's the probability distribution output of a much bigger entangled state that we have prepared here. And we always see that despite noise, of course, the bigger, the more noisy this state will be, but despite noise, we still have the biggest 2 spikes in the expected states. So this is also a very interesting property, and you have seen with Danny yesterday that superposition and entanglement can play a very important role in quantum algorithms. So those are really the 2 fundamental properties we care about. But now I have a question for you, and I've seen actually some of the questions being asked already today. So now that you know how qubit behaves and what they are capable to do when, let's say, manipulated with some specific gates, would you know how a qubit looks like? If you had to guess, and I have 4 guesses for you today. So go on and write on the chat which option do you think is the correct one. So first option is a photon. Do you think that a photon could serve as a qubit in quantum computers? Or you prefer the electron? Actually, you think it's a better option for serving as a qubit. You can also have an atom, if you like, as a qubit, or an artificial atom. So pick your favorite one. Let me open the chat to see. Atom, electron, photon, electron, photon, photon. Photon has a lot of popularity. Artificial atom, I saw. Ion for trapped ions, very good. Photon, artificial atom. Okay. That's great. But I also see that someone is actually very well prepared here, because they are saying that actually all of them can be used as platforms to create qubits. So you are totally right. We have photonic quantum computers. We have quantum computers based on neutral atoms. Someone mentioned also the ion-trapped quantum computer. So you really have a lot of different types of quantum computers. And this is what really gives us I think, the most fun in the community. But today, we will focus actually on one of these four type of qubits, and it will be the artificial atom, because this is actually the type of qubits that we are fabricating here at IQN. Great. So how are these artificial atoms qubits called? Those are the superconducting qubits. And I think most of you will be familiar with what a superconductor is, but I think a reminder never hurts. So many years ago, it was actually discovered that some metals kept at very low temperatures, they could behave in an unexpected way. That is, they could conduct the electric current without any resistance. And those metals were called superconductors for this reason. But later on, in the 80s, actually someone discovered something even more exciting. So while working with small electronic circuits with superconducting elements in those, scientists discovered that these electronic circuits could behave like an atom, like an artificial atom. And this is the moment where actually the superconducting qubit was born, because the superconducting qubit is nonetheless a superconducting circuit. But we had to wait some years, like 40 years more or less, to make use actually of this discovery. And here we are today with the superconducting quantum computers. So the superconducting quantum computers are quantum computers using these artificial atoms as qubits. And here in the pictures, you actually see two of our superconducting computers that are different between them for the number of qubits that they have in the QPU. And you will be surprised, maybe or maybe not, to see that actually there is a lot of machinery around the QPU. And I'm actually curious to know whether you have an idea where the QPU here is among all these instruments. We will have a closer look to it, but yeah, just try to imagine where it could be. And here in the middle, I have put this picture because I think this is one of the most common and famous images if you look for quantum computer on the internet. And I want to give you a very basic intuition of what is going on here. So let's take an inside look to a superconducting quantum computer. First thing is, as we already said, the superconductors, so these metals that cool down, present these exciting properties that they can conduct electric current without any resistance, they need to be cooled down. This means that superconducting quantum computers also need to be cooled down. And this is done through a cryogenic cooling process, usually achieved through, for example, liquid helium here. But then you also have a lot of cables here. Those cables we will actually see in the following of the presentation, that these cables are needed to manipulate our qubit in the QPU. So those are in particular microwave cables, some of them also superconducting. And then you have some magnetic shields. So in general, the qubits are very easily perturbed. So we really need to make sure that they are shielded from the external environment so that we can preserve very important properties of qubits, of quantum systems in general, like the capability of entangling them or putting them into superposition and preserving this quantum characteristics. So this is all actually only one part of the things that are used to manipulate the qubits in the QPU. But last but not least, the QPU. So the QPU actually is here at the bottom of this like golden cylinder. And it is, of course, the heart of the quantum computer because it's where the qubits are and where all our algorithms are running. But thanks to all the external driving and the cooling and the electronics that are around the quantum computer. So also to answer many questions in the past days, no, you cannot at present really fit a quantum computer at your home. Let's say you really need labs and centers that are that can host this type of machinery. Okay. So now that we have discovered where the QPU is inside this block, then we actually want to do, we want to go still a little further. We want to see inside this QPU. And to do this, we have constructed this interactive for you that represents a demo chip. So this is not how the chip would look like precisely in reality, but what is important is that it has all the principal components that we really need to make a superconducting QPU. So I encourage you now to go to this URL here in the bottom or scan the QR code. It should work. Yeah, I hope. And also, if someone can please share this this link in the chat, that would be awesome. Okay, it's already there. Thank you, Danny. So what I want you to do is not like suddenly to understand everything that is in there, but you have this magnifying glass and you can explore a bit this picture, let's say. And then you also have some descriptions of the elements that are there. And I will leave you some seconds, then I also go there so that we can go through them together. Okay. So here we are. Let me scroll down a little bit. Great. So, okay. First thing first, here we find back the little drawing that I had put at the very beginning for this artificial atom qubit. This is indeed taken from here, and this is what it represents, a qubit in this demo chip. And you can see that there are two lines kind of directed to these qubits that we will see in a moment. And then another very important part of this chip is this kind of wavy line here. And we can actually find some answers if we still scroll down where these are defined. So the qubit, we already know what that is. But for example, let me go to this wavy line. This wavy line represents our readout resonator, and this will be very important for our lab today because actually this will be about the readout of qubits. So what happens when we actually measure a qubit at the physical level? So then about the two lines that I was talking about, there is one drive line that we will also see what is useful for, because we will see how the gates are actually implemented on a qubit. And last but not least, there is the flux line. The flux line controls some other properties of the qubit, like their frequency. And this will become clearer also in a moment. Okay, so let me go back to the slides. And let's take. Perfect. Okay. So let's go on. What did we find about this QPU? Each qubit in a superconducting QPU will have the following controls. There is the readout resonator here highlighted in blue that is used to infer the qubit state. So when we want to know something about our qubit, we need to measure. And this is what happens here with the readout resonator. Then there are the drive lines, and in particular, we will see how they are used to perform single qubit gates on the qubits. And then there are the flux lines, and this is to control the qubit, but also the coupler frequencies. And then here you see maybe a new word actually next to the drawing of the qubit, this Transmon. So the Transmon qubit is a specific type of superconducting qubit that we are using in our technology, but there are other type of superconducting qubits that could be fabricated. So this Transmon for us is equivalent to the qubit that we are using. Okay, so now we start to go a little bit more into details, but I will still try to give you really an intuition of what is useful without going too much into the physics. So we have said that an artificial atom that we are using as a qubit is actually a superconducting electronic circuits. So to start with, we will have something of this type, where here this is an LC oscillator, but we do not really care about the details of the circuit here. And any system in physics, if you had like any physics lecture, but even if you haven't, you can describe the energy of any system. And this is done with a quantity that we will call here Hamiltonian. So if some of you have taken this physics course, they probably remember the example of the pendulum. And there you will probably also remember that there was this potential energy that looked like this parabolic here behavior. So what we have is something similar. So here the QHO stands indeed for quantum harmonic oscillator, and the energy of this circuit can be described as this model, which is very convenient. The very big difference that we have between the classical and quantum systems is that usually in classical system, the energy is spectrum is continuous. You can be in any energy configuration. This is not the case in the quantum systems. You actually have some defined energy states or energy levels in which your system can live. And yeah, so this is quantized spectrum of energy indeed. And what is important here is to observe that the space between this permitted energy levels is the same. So we will have this quantity throughout all the levels that are infinite, and this is a uniform spacing. Why is this important? Because actually what we need to do to isolate our artificial atom. Remember, we talked always about two states of the qubit, 0 and 1, but here we are seeing many. And also in the questions, we had in the past days, I also read about why are not we using qubits, for example, that would be including the second level here. Well, this would be possible, but we are focusing on qubits, so only two levels. And we can achieve this isolation of this lower energy level here, introducing another element in the superconducting circuits, which is usually a Josephson junction. So we don't need to know the details of what this junction is, but what we need to keep in mind is that this element introduces some non-linearities in this spectrum, and this is actually what gives us the possibility to obtain something that is not uniform. So here, the spacing between the energy levels will not be the same anymore. And we have actually achieved what we wanted, because now these two levels are represent our two-level system, which is well isolated from the other energy levels. So this, what we call anharmonicity of the oscillator, the fact that we do not have this red curve here dashed anymore, is what gives us the two-level system we can play with. Okay, so hopefully this was not too much. But now that we know what a qubit is, so we have seen that is superconducting electronic circuits where we introduced some non-linearities and we isolated the first two-level energy level of this quantum system. So this is what constructs our artificial atom. And now we want to understand how we can manipulate this. We have already done this with on the surface, let's say, with our quantum circuits. We know how to apply gates, single qubit, two qubit, but how to manipulate them at the physical level. And to do this, we actually need to drive the superconducting transmon qubits with some microwave pulses. If you remember when I showed you this inside look of the golden cylinder, I told you these cables are microwave cables, and those are the cables through which we drive our qubits, sending pulses. And also the drive line that we observed on the demo chip, this is actually the line through which these pulses can interact with the qubit on the QPU. And again, here we have an Hamiltonian. So this time, this Hamiltonian doesn't describe only the transmon, so not only the qubit, but the interaction of this qubit with the microwave pulse. And we have a term that is still relative only to the qubit, but we have another term which is more interesting for us that gives this, describes this interaction, what happens when we really send this pulse on the drive line of the qubit. And this is what is called a Rabi oscillation term. So actually one experiment that scientists can do to understand whether they have prepared in the lab the qubit they wished for is this Rabi experiment. And here you see that we observe this oscillation. So these dark and bright lines, those are the oscillations between the 0 and the 1 state. So you can see that your qubit is actually driving these oscillations only between the 0 and 1 state and not going to any other higher energy level. So you were able to isolate your two-level system. But now we want to actually have a better, like, let's say, a more useful form of this expression that, let's recall, describes the energy of our system pulse interaction. And if we change reference frame, and we don't care about the mathematical operations that we need to do that, we can transform this equation into another form where we just made an assumption. Here, this omega and nu, those are the two frequencies of the transmitting qubit and of the pulse. So we have put ourselves in the situation where those two coincide. This is usually referred as resonant. This is the resonant case. And why do we like this equation more? Here you can see that we have two terms appearing, one sigma x and one sigma y. You probably do not recognize them in this form, but sigma x and sigma y are the Pauli x and y gate that this morning before Danny was talking about. So the rotations that you have in this native gate set of IQM quantum computers. So actually here, we have reduced the expression to only sigma x and sigma y, so x and y rotation. And in particular, we can see that we can drive quite easily x and y rotation if we play around with this phi angle here. So phi, if I put it to 0, this term will disappear, the term with a y, and this will give me a rotation around the x-axis. But if now I put phi, for example, I set phi to pi over 2, then this term of x will disappear, and then I will have gotten a rotation around the y-axis. So this is how qubits are actually driven to rotate around the axis that we want. So single qubit gates, we are used to visualize them or their action more precisely on the Bloch sphere. We know that this point on the sphere represents the state of the qubit, and each time I manipulate it, so I make it rotate, this will change position on the sphere. And this is equivalent to applying a drive to our qubit to make its state rotate at this moment around the x or y axis. So this is why our native gates also are rotation around x and y. The example, the simplest example we can think of is the X gate that we have seen many times during these days, which is an analog of the NOT gate in classical logic gates. And the action is to flip the qubit state. But what it means to actually apply an X gate. So we know that it means to apply a pulse, a microwave pulse that interacts with our qubit. But this pulse has to have a definite amplitude and also a definite length in time. It doesn't last forever. So if we manage to find the right amplitude and length, then we can perform an X gate. But what we know about the X gate is actually the rotation that it makes. We know that it flips. This gives a rotation of pi around the x-axis. So we would like to connect this to the angle that it rotates on the Bloch sphere. And this is possible for this equation. So we do not care about these constants here. Those are constants relative to the specific superconducting circuits that you have fabricated, but those are fixed. Let's say we can forget about them, but what we care about is this quantity inside this integral. So t here is the length of the pulse that I was talking about, so the time we make the pulse interact with the qubit, but this s of t prime here is the envelope of the pulse. So we can give actually a form to the pulse that we want to apply. So this envelope will describe actually the waveform of this drive pulse. And if we solve this equation, then we get the angle of rotation on the Bloch sphere. And so if you would like to implement an X-gate, what you should do is to solve this equation setting this equal to pi, because you know that this is the rotation you want. And now we can actually go to our second interactive of the day. And I have a question for you that you can then explore on the interactive in a moment. So let's imagine that you have found the right amplitude and the right length of this pulse to implement an X-gate. So to implement this pi, rotation of pi, then would you know how to implement actually the square root of x? So first thing to discover is how do you get, playing with the amplitude and the length, how do you get an X-gate? And second is how can you get a square root x gate? So let's go now on the second interactive and find your answer playing with this amplitude and length of pulses there that will be mimicked also on the Bloch sphere to give you an idea of what is going on. So let me know if you share the link in the chat.
Yeah, this time Danny was faster than I was. Last time I won.
Perfect, thank you. And let me also go there, but I will not spoiler the answer, I promise. I will leave you the time to find it. And if you find it, you want to write it on the chat, go ahead. You can actually zoom out a little bit if you want. Here is, yes, you can move this around. And also here, you can see what the amplitude does and what the length does to the pulse. And remember to reset to 0 if you are like doing different attempts to find your answer. Let me check the chat. Okay. I see some answers. Okay, great. Since I see the answer, then let me go to that too. So yes, we can, for example, put our pulse length to 30 nanoseconds and the pulse amplitude to the max that here is represented by 2. And let's see what happens if I apply this pulse. So the qubit actually, the state of the qubit rotated of pi around the x-axis. So this is exactly what I need to do if I want to obtain the X-gate that flips the state from 0 to 1. And now, if I'm looking for actually the square root of x, let me reset to 0 as I suggested to you. Then let's see what happened. Okay, so we actually obtained a rotation of pi over 2, which is what we wanted, by halving the amplitude. Okay, let me go back to my slides. Great. So we have seen that the X-gate can be achieved putting these two parameters. And the square root x gate, that is a rotation of pi over 2, can actually be achieved halving the amplitude. I've also seen in the chat someone writing that it was about halving the time. So this is true for a very simple model of the waveforms. If you have like a constant waveform, like a square, then this is definitely true because the dependence is linear, both in amplitude and time. But this can be lost actually with more complex models of these waveforms. So you really need to know what is your envelope to understand the dependence on amplitude and time. But in simple models, that is actually true. Okay, so yes, hopefully this is what you have seen also playing around with the applet. Okay, so we have seen how to create an artificial atom as a qubit, to use it as a qubit. We have seen how to drive it to perform rotation that we wish on the qubit. And now, how do we do this actually on IQM quantum computers? And I like this animation a lot because it's simple but gives an idea of what happens every time you press a button on your laptop and you send something to a quantum computer. So we find back our beloved circuit here. And so the first thing that happens when you compile, when you send your request to the server, is that this gets compiled, and we will see what compiled means, into a sequence of pulses. So into a sequence of all these operations that we have done before. Then these pulses interact, they are sent into the refrigerator because there is where the QPU lies. So here is what is inside the refrigerator. And third, the pulse interact with the QPU that is at the bottom of this cylinder, and they interact with this Hamiltonian that we have seen before. And then, of course, you need to kind of read the results of your calculation, and then you can process them on your PC again. So we will see more of about this compilation, but also about this readout, as I had already anticipated. So we are slowly transitioning from a gate representation of our quantum operations to a pulse representation of them. And as you can see in this very nice drawing from our colleague, this is a long way. So usually we just stop here. So we have an idea of an algorithm, we write it into a quantum circuit. We transpile, as Danny showed us this morning. So we kind of translate it to something that our computers can understand. And then that's it. Then we do this, we see up to this point, and then we jump here where we have our results, our strings of zeros and one, and we do whatever we want with these results. But in the middle, there is all this way to go down and up again. So now we will focus on this compilation step to understand what happens after transpilation. And we have a software that our colleagues in IQM developed that is really made for you to do that, which is the PULA package that stands for Pulse Level Access. So now we are thinking about an access to the quantum computer at a lower level than the gate one. And what you can do with it, you can compile a quantum circuit into a pulse schedule. This will be our first exercise today. You can also define and execute custom pulse shapes. As I told you before, this envelope shape is actually playing a role into the translation of the pulse into this rotation. So this is also an important part. And then another thing we will see towards the end is that you can actually access and modify the calibration data that are used for your circuit execution. And why would you want to do that? Let's imagine that you are a quantum engineer or a quantum scientist, and you are working maybe on the hardware side of things. So you need to calibrate the QPU. That we will see what this means. Or you want to be sure that you have, for example, prepared a good qubit, as we have seen with this Rabi oscillation. Or you can also ask yourself whether the results that you're getting would improve if you change something at the physical level, like the waveform shape. So those are all possible scenarios that a quantum engineer can face in their day-to-day job. Okay, compilation. So compilation is actually the action of translating this high-level quantum programs or circuits that we have written so far into operations that the quantum processor can actually execute at the physical level of the physical qubits. So the compilation is really an extra step of translation after transpilation that goes lower into the physical level of these superconducting quantum computers. Okay, so first small lab for today will be actually to take the usual circuit that we are used to, the one to construct a GHZ state, but this time we compile it into pulses and we see what this looks like. So let me actually go to the lab. Okay. Thank you for the link in the chat, guys. And hopefully my runtime didn't crash, so we are actually up and ready to run things already. Let me see. I need to, okay. No, unfortunately, I will have to reconnect. So we will go through this once again together. But this is probably a good thing to give you the time also to install things. But as Danny stressed already this morning, please do not focus too much on debugging the errors if you're getting any, but rather follow the explanations with me, and then you will have the occasion to debug later. Also on Discord, you can compare your results. So, as I said, the goal of this small first lab is to compile a quantum circuit into pulses. So let's pip install. Here, I'm installing this specific version of pip because I'm working with this Pula package that we have seen before that requires for me this version of pip. Maybe it is safer if I copy. Okay, let's start it anyway. Okay, so just to give you a heads up, I will have to restart actually my runtime twice because once for this cell and once for the other cell. So if this happens to you, that is normal, I would say. And I didn't check my runtime, but it should be already the good one. So keep in mind to set the runtime version to this one, 2025.07. Otherwise, you will have more troubles installing the packages. Okay, this will take a bit of time and we will see the first restart request and we will hit yes. So we will not cancel it. And for the people who were actually worried about not being able to run anymore on Garnet or Emerald for credits, actually you will have the possibility to run the second lab that we will see together on Sirius because that is fully based on Pula, so that will be actually possible. Exactly. So restart session and hit again. This was the first restart. As you can see, you're not the only one that have to actually debug for running some quantum jobs. So that is part of the experience. I'm checking the chat to see whether there are questions. I don't think so. Okay, and it's installing. You see here I specified actually all the versions of the packages that we are going to use to make sure that the examples work for you too. So hopefully this reduces a bit the errors on the versions of packages that you were facing maybe in the past days. Okay, we are almost at the end, but we will have to install also CRISP because we will construct our circuit as you did in the past days. So I think the interest of this exercise is really to see that something that you have already learned to do, that is this GHZ state preparation in CRISP, then actually gets compiled into pulses. So I think that is fun to see. Okay, be aware that there will be a second restart. And yeah, so maybe in the meanwhile, I can actually talk to you about this first cell. So here we will import Pula, this pulse level access package. And again, we have the API token as before, where you were using only CRISP or Qiskit. And again, you have the URL of the machine of the QPU that you want to use. And this time, the difference will be this line here. So here we are calling this standard compiler. So remember that we are going to do a compilation exercise. So we need a quantum compiler. And the standard one has already some default settings that are decided for us, which to start is perfectly fine. So we will initialize this. And this compiler is an object that contains all these settings and also available operations for us in the specified QPU that we call here. Okay, second restart. We are close to the end of the installation. And I think that for the interest of time, for the next lab, I will guide you through maybe the results and then leave you to experiment as a homework. But let's see what we managed to do. Let me prepare my token actually. so that when it asks for it, I'm ready. Okay. Oh, we are ready. Great. So let's import for the first time this Pula compiler. I will copy paste and hit enter for my API token. And I didn't check whether Garnet was busy. Let me check quickly the queue. Yes, there is no queue. Perfect. Oops. Let's go back. Okay, so we are now connected and we have initialized this quantum compiler. And now we need to write this quantum circuit. So we import the quantum circuit from CRISP and we use quantum circuit. And here in this case, I put 3 because, yes, I imagine this to be the free qubit GHZ state. And then, as you know for sure now, you have to put the first, or whatever qubit in the superposition state through the Hadamard gate. Then we use the CX operation on this qubit and the first one, 0 qubit and the first one, and then again, oh, sorry, we have this CX between 0 and 2 this time. And then what we need to finish off is the measure. Otherwise, we cannot infer actually the state, the output state of our circuit. Okay, let me see if everything went well. There is a runtime warning that I will ignore. And this print should give us the literal drawing of the circuit if we have prepared it well. Great, okay. So we see the Hadamard, the 2 CNOTs, and the measurement on all the qubits. So that looks fine. And what we will need to do here is to transpile this circuit, as Danny showed us before, to actually be able to run this on the specific QPU, because we have seen there are connectivity constraints and also native gates constraint. And we can do this by calling the transpile. And here inside the brackets, we will call this backend equal backend, because here I called it the same. So this is the option to specify towards which backend we want to actually make the transpilation. It's taking some time, but hopefully it's smoothly running. Okay, so you see here that the circuit was quite simple. So we do not have that many operations or gates in the circuit, but now we see all the qubits in the QPU involved after transpilation. Okay, and this step, so we need still to translate this or convert better to Qiskit, because the Pula visualization tool actually understands the instructions in Qiskit. So you can do this. It's available in CRISP with this toQiskit function, which is only 1 line. Perfect. And here you see those are already filled in for you, because that is a bit more technical part to serialize these instructions in the circuit and rename your circuit, actually like constructing a new circuit object with these new instructions here. But what we can do here is to call the compiler So remember at the beginning, we had defined this compiler here that is suggested to. And we call the function compile because this is what we want to do. And also, we put this IQM circuit here that we have constructed. So now this step is really the compilation of our circuit from gates to a sequence of pulses. Okay, and we call here this playlist is actually this sequence of different pulses that we have in the compilation. And let me see if we are able to actually visualize this. Okay, great. So this is how it looks like. There are many lines here, and we can actually observe them. So we transpilation chose for us qubits 13, 8, and 3. And so we will also see the connections that are this TC. Those are the tunable couplers. So the object that is connecting the two qubits 3 and 8 and 8 and 13. And then we also see here free objects, free lines that are for the readout, because remember we were measuring all the free qubits in the circuit. But now if we go a bit, we can zoom with this. We can zoom within this. Too much. So there is a wait at start operation to be sure that everything starts properly at the same time. And then what is interesting for us is this object here, for example. This is called an IQ pulse. So this is the pulse that actually drives our qubit. And if we scroll down, we actually can see what is the amplitude and the length of this pulse. So those plots are actually corresponding to what we were seeing in this animation that we had before with the pulse and the Bloch sphere. So this is really what is happening in a quantum superconducting processor. And for each qubit, of course, you will have slightly different lengths. So here you can see it lasted 28 nanoseconds instead of 20. And you have also some virtual operation that we didn't go in, but if you want to perform a Z rotation, you can actually perform it in a virtual way. And then you have some weights and some readouts. So you can continue playing with this. I think it's interesting to also see the difference with the 2 qubit gates. And I will actually reshare my slides where I put some of the outputs that I obtained previously. Okay. Let me go into slideshow mode. Great. Oh, yes, sorry, I explained it to you without showing the slide. Okay, so this is a snap of the circuit that I had obtained previously. And here, for example, I selected this pulse to be shown that looks similar to what we had in our execution right now. Then here I highlighted the pulse that corresponds actually to the 2 qubit gate that we see in this circuit. And you can see that it lasts longer, usually. And then also the readout. I highlight this here because the lab now that we will have is actually about how readout works. And yes, let's jump into some small introductions to the task, and then we'll see the lab. So what we need to mention here, and I actually have already mentioned this previously, is calibration. What does it mean actually to calibrate a QPU? And this, in one sentence, we could say, means to find the right parameters for the QPU to maximize the performance of it. And the calibration is really the process where you have no idea what the right parameters are and you start from scratch. But what is actually done every day for quantum computers is recalibration. That is a small subset of this full calibration of a QPU that is done at the very beginning, and it runs periodically to avoid some errors that could arise during different times. An example of it is that you want to find the frequency of your qubit. Then you can drive the qubit at different frequencies, and then you can stop when you see a signal in something like this. So here, the qubit frequency would be something around 3.9 gigahertz. So this is a typical recalibration experiment that you can do. But actually, this is an example of what you would do a bit more rarely, because this means that you have changed the flux. And if you remember, we have talked about a lot about the drive lines, but less about the flux, because this happens more rarely in reality. Okay, and there are, for each operation in your circuit, there are different parameters that you could care about. And for example, for the single qubit gate, this finding the frequency is only one of those. But then you have many other experiments that you run in this recalibration to make sure that your qubit are always up and running at their best. So all these parameters that you find, that we were discussing before also in the chat, in the specifics of our QPUs, the characteristic times, the single qubit error, the CZ gate error, those are all the results of this series of experiments that are run every day on our QPUs. Okay, so the readout on superconducting QPUs follow a model that is called a dispersive model. We do not need to go into too many details, but just to have the name in mind. And so we have seen that qubits are coupled to the resonators that are used for readout. And this line that is here highlighted in blue actually lets us address multiple readouts with a single line. And this is very convenient. And then what do we measure? I saw one question about this. What do we actually measure to do the readout? What we measure is this shift. So we know, based on the physics of this interaction, that the frequency of the resonator, so of the readout resonator, will be shifted, and this shift depends on the state of the qubit. So basically here, the orange points correspond to the 1 state, while the blue points correspond to the 0 state. And thanks to this shift, we can know whether our qubit was in state 0 or 1. So this is the quantity. It's this shift delta omega that we measure. So yes, a microwave readout pulse is sent nearest to the frequency that we know the resonator have, and then measuring the difference after the interaction, we can actually read out the qubits. So this is what we are going to try and visualize a bit more. So how readout works in superconducting quantum computers. Okay. So I actually have only half an hour, but let me try. I guess also my second runtime, unfortunately, is not available anymore. So let's, oh yes, sorry, I forgot to ask for the link in the chat, but I'm sure that that you have it. Let me check. Yes, we are in the correct runtime type. That is good. And we have the same comments as before. Yeah, basically the same package. We added this matplotlib because we are going to plot some more stuff. And here, actually, we will code exclusively in Pula. So there will not be anymore the notion of the gate as you have seen until now. So in the exercise before, what we did was to have this compilation, this translation, but we still used to construct the qubit, the quantum circuit as we knew. But here we will see that we can define operation differently. And let me actually, while we install thing, I'm still allocating runtime. It's a long way there. Let me go into some of the details. So here, the first part is the same. We have seen this in the previous notebook. And here again, we will get this standard compiler because this is the default and we are good with it. And then here, I encourage you after this session to take back this notebook because we also have put some links there for you to deepen your understanding because, of course, it is not possible to go into the details of the interaction model between qubit and pulses, but you can have a better idea if you also visit the links that we have put throughout the documentation, so you can actually read this more carefully. But what I want to stress here, oh, probably pip got installed. Just 1 second. Yes, let me hit this. And while it installs, we can comment here. So an important thing is that when we get the raw result of a measurement, this is not the nice 0-1 label that we are used to. So today, in this lab, we will try to understand what actually is the raw measurement result that we see after measuring a superconducting qubit. So we will, as it is highlighted here, we will not perform a thresholding. This means that to translate from this raw result, which is a complex number, to the 0-1 label, usually what is done is a thresholding operation. So everything that is above a certain threshold will be 0 or 1. And to see the different results, we will also prepare the qubit in 3 different states: the 0 state, the 1 state, and the superposition state. And also here you have links. Let's restart. Yes, thank you. And this should be only once this time. Great. So while it installs, let's already think about how we can prepare the qubit in these 3 different states. And here you have links for the documentation to the pulse level access packages of IQM. So to implement, actually to prepare a state and then measure it to see what the outcome is, we still need to have the definition of the gate that we want to actually implement. And in this case, it's this expression here. You can find that we find back this cosinus of phi and sinus of phi that we had in this Hamiltonian expression that, if you remember, we have seen before. And we will tune these angles phi and theta to achieve the state preparation that we want. Okay, so you can see here we are initializing a list of an empty list of circuits, and then we are calling this preparation state 0, state 1, and superposition, which is quite self-explanatory. And here what we need to do is to insert a list of angles that will give us the correct preparation. So for the state 0, we actually just input a 0. For the state 1, we saw this. We know that actually we want to flip the state. So I'm going with a pi angle. And for the superposition, we will have pi over 2. It is still executing, so I cannot still run this cell, but already we were able to do the first to do. Okay, it should be almost done. Okay. And as I suggested to some of you yesterday, then to verify your installation, you can use this command here that calls all the IQM packages that you installed so that you can verify if the installation worked correctly. Great. So let me actually, don't know if this is the good one. Okay. So now we should be able to run this. I will be asked the token again. Yes, I can copy paste and hit enter. And if Garnet is not too busy, perfect. Okay, so let's see whether we can now run. First, we initialize the compiler as we did in the previous notebook. And then we define our operations. Okay, perfect. So here you can see we have the operation name that is PRX, that is the gate here reported in this expression here. And then we have only one other operation, that is the measurement operation, because that is what we are interested in. And for this state preparation, the phase was set to 0 for all the states. Great. So here are some more details about the calibration settings of the measurement operation. You can actually have this for all the operations that are available on the QPU if you are interested to have more details about it. Here, what we are interested in is this implementation constant, because this is what we will use, that is the default implementation. And what we are going to change, so for the first time, we are actually going to change one of the default settings, is this acquisition type. Because as I told you, we do not want to do this threshold. Otherwise, we would again see only 0 and 1, but we want to see the raw result. And to do this, we need to change this acquisition type from threshold to complex. So here I had left you a small to do. We can just put the string complex here. Great. And I've left you commented a way to do the same thing on Series. So if you cannot run on Garnet or Emerald, this is the way to go on Series. Okay, I have a type error. I probably typed something. Sequence item 0, tuple found here. Okay, let me quickly check. What is the problem here?
You should be able to use the same code that is used for IQM Star as well. But maybe for now it's just easier than to switch to Star.
Let me just...
But I guess it's the way qubit is written. Qubit is a tuple, and the brackets are the problem around qubit.
Okay. Yeah, it worked before. But yeah, I think this is exactly... yes. So would this just be... No.
The round brackets need to go away,
Okay.
I think.
No, I think for the locus, actually, they do need brackets, but yeah. Okay, let's try series then. Sorry for that. Okay, I will have to copy back my token. Great. Okay. Let's redefine the compiler and the operations. We can again visualize this. And now we should comment this line here and try this one. Okay, seems this succeeded. Okay, perfect. Thank you, Stefan, for the tip. And so now we need to actually compile this the circuits, and we have already seen how to do this because we can call the compiler.compile. And since this time our circuits are already in a list, we will not put the list brackets around, and they were called circuits simply. Okay. Here we have an error. I've never faced this error before. Let me try. Aha. I think this was the problem actually before. Yes, probably this. Sorry, yes, let me check because I think there should be some. Oh, yes. I just jumped one step. So here, this is not the right way of calling the qubits. We need to actually call them as a string. So let's say here we want to manipulate qubit 1. It could be whatever qubit in the QPU. So this is the way of calling the qubit. And I think this was the error before. So once again, sorry, let me go back to check so that we can verify if this was the error we got before. Okay. So we go again with this, we comment here, and yes, okay, cool. Sometimes one error is not enough to understand what the what the problem is. And the job is now already done. And let's analyze the result. Okay, so now it is, I think, time to stop and comment this result so that you can then continue by yourselves with the other steps in this notebook, because I think it's important that you know what you should expect, because all the rest of the notebook will be to play actually with the calibration parameters to break this. So if you don't know what to expect, then it is difficult to understand whether you broke it enough or not. So here you see two clouds, and you see that the blue dots correspond to prepare the zero state, and the orange ones correspond to prepare the one state. And then you see that sometimes it can happen that they are not very well clustered. So we can see these two very big clusters, but if we look very closely, we can see that there are some orange dots here and some blue dots here. This is the result of having some noise in the quantum computer. but the overall behavior is quite good here. So this is what we would observe for preparing a state in a 0 or a state in a 1. But if you remember, we had prepared also the superposition state. So if I change here, let me quickly change this. Should be 2. This should go away. And yes, let me just call this state 0, but it will be the superposition state. And let me see if this works. Cool, yes. So what we observe here is that the position of the clusters are actually the same. So this, remember, this is not prepare 0, but the superposition. So the clusters are in the same position as the 0 and the 1. And there is no continuum of points between the two clusters. Of course, there are some dots around, like here in the middle, but it's not a continuous. It's really the same location that we were seeing before. Okay, so I think now, in the interest of time, it is good to stop at this point. And let me go back to my slides to actually spoiler you a little bit what you should expect. Okay. So on the left, you have the result of a good calibration. So it means that overall the qubits are working fine and the errors are quite manageable because yes, we have some points in the wrong clusters, but the overall behavior is good. But what if you change the calibration? This is what you will do in the following as a homework, playing with these parameters of the calibration. You can see here in the first plot that actually your clusters will not be very well separated anymore. And here it is difficult to use the same argument as before. Yeah, some points are in the wrong cluster, but here they are really overlapping. So this is not a good calibration. And here something even stranger is happening, tuning a different parameter, which is the clusters actually gets a bit like deformed. They change shape and they seem like to have different positions. This is also something that you should not observe. And it is very useful because if you see these results, then you know that there is some problem in the calibration and you should go and recalibrate your system. Okay, with this, I think I want to pause for a moment to see if there are some urgent questions that need to be answered before concluding the last session of the Quantum School. And yes, I hope this was fun. So let me, yes, get back here. See a lot of activity in the chat.
I think people want to see some of the settings for
Yes.
getting the changing the threshold.
Yes, definitely. Definitely, yes. Let me go back. Let me go back to the lab. Yeah, it is true that there are a lot of parameters, so don't get scared about that. Okay, what we did here, I think this was the question. What we did here was, okay, let's look at what the measure operation looks like in the default setting. And to do this, we can call this command here, print implementation trees, that will show us, okay, the measure implementation default to constant. And then there are a lot of other parameters. There is duration, frequency, phase, amplitudes, and a lot more. But what we are interested in is this integration threshold, this acquisition type that is connected to the threshold, because we can do two acquisition types. We can do the threshold one, that is the default because we want actually our user to get what they're used to, this 0, 1 label, because this is what we usually understand. But here we wanted to go into a more physical level. So to do that, we need to change this threshold. We want to avoid thresholding, and we want to go back to the raw measurement result, which is indicated with this complex name here. So what we did here then is, what we are seeing here is, please change the calibration settings of this gate, the measure gate, in the constant implementation, because this is what we have. For the qubit that I'm manipulating, the qubit 1 in our case, and here finally the acquisition type, that is the only thing we changed from threshold to complex to be able to see this cluster of points. And let me check. Yeah, I think this was the question. Okay. If you spot any other question, please. Could you show what you did in the last cell? Yes, of course. The last cell will be this one, but let me go maybe back to the 0. What I did actually was only to change this to show you also the superposition state. So if you remember in our state preparation, we had 3 different states. We had the 0, the 1, and the superposition. And this index here index the different states. So we will have a result for the 0, a result for the 1, and a result for the superposition. So actually what I did here was just to show you the result 2 that was corresponding to superposition. But if we want to see the original result, this was the original result for 0 and 1. So I hope I answered your question. Yes, when I changed the 0 state to 2, yes, that was only to show you an extra state. This amend calibration for gate implementation, you should read this in a simpler way as change this parameter of the calibration I'm interested in, that in this case for us was the acquisition type. I think I just want to conclude with some thank you remark to all of you. This was an amazing experience for 3 days, and a lot of you have asked us how to continue learning and what you could do next. I think a very good start is to continue learning actually on the IQM Academy, because there you have 3 different levels of modules that you can learn from. There is the beginner, the intermediate, and the advanced. So already if you manage to go all the way up to the advanced modules, you will be in a very good starting position. Then, for sure, you can also learn more from the hands-on. As you have seen here, we really stress the importance of running things yourself because it's really the most valuable experience. And for that, we also have on the Academy not only the learning part, but also the examples and the tutorials that we have been showing here. But we have more advanced. So as you progress in your learning, you can also progress with your algorithms experience. And for those of you who have not yet done that, please follow us on social media like LinkedIn and YouTube. On YouTube, you will find the recording also of this session later today. And you can always stay up to date with our next events. So thank you everyone really for participating to the IQM Quantum School. We hope it was a wonderful experience for you as it was for us. And I also call Danny and Stefan if you want to give some concluding remarks now. I see that you're still busy answering questions. That is awesome. But yes, please.
Yeah, Nadia covered most of it, but it was a really great experience running this and interacting with you all. It was a lot of fun for us, and we hope that you've gotten excited about quantum and are now well positioned to really dive more into the topics that are most interesting to you.
Indeed, I can only agree. It was a pleasure of hosting you, of having you. I think one of the best ideas we had was actually to enable the chat right from the beginning. So we could see your excitement, and yeah, it was a fun pleasure. And I think I hope we see you again at a future event. And with that being said, enjoy your quantum journey.
Thank you, guys.
Thank you all so much.